So our last part of this chapter is going to look at what are called hybrid orbitals. Okay, so hybrid orbitals come from when we have very, very poor overlap. So for example, let's say a hydrogen atom was going to bond with an orbital of another atom that was the 2px. Okay, so if we try to do an overlap here, we see that these are the same phase, but this is not in phase. So we have two sections that are in phase, and again, this and this would overlap, not in phase. So if we looked at the bonding, we'd have this area here where we'd have constructive overlap, and then over here, since they're not in phase, any overlap we'd have here would be destructive. So the bonding here would be very, very poor. Okay, so very, very poor bonding. So kind of to counter that, atoms typically form these things called hybrid orbitals. So what we're going to see, a hybrid orbital will be mixing of different S and P. Okay, so we're going to see different hybrid orbitals depending on how the S and P are mixed. So essentially one thing to note, and we're going to see when we make a hybrid orbital, we're going to see one end, one tail of it very small and one tail very large. So instead of going from the symmetric where we have this phase and this phase being equal, if I could draw properly, we're going to see that we're going to form these hybrid orbitals where we have an increased lobe to increase the chances of constructive overlap and putting our out of phase sort of in a smaller area. So you could imagine if this one had a giant hybrid orbital here, we would have much better overlap here. Okay, so let's take a look. So let me get our lighting correct here. So this is also in your module. So we have hybrid orbitals and molecular shapes. So kind of think where this whole theory of hybrid orbitals came from was by actually looking at the bonding angles of a lot of our shapes. So for example, we've looked at this a couple of times. So we said this is a 109.5. So how in the world do we form a 109.5 given that we're using S and P orbitals to do this? So if we look at sort of traditional S and P, S is this sort of nice spherical shape, and our P's we have in these lobes pointing along X, Y, and Z. If we put them together, we get PX, PY, PZ. Okay, so all of our angles separating all of our P's are all 90 degrees here. Here we can bond at any angle because it's a sphere. So we have any angle that we could use here. Okay, so how does the arrangement of this give us 109.5? Or if we had a double bond, how does it give us that 120? Or if we have, again, the trigonal planar or a linear. And so really the only shape that would make sense is we could get a linear. We could have sort of one end and one end. Okay, so turns out that we don't really use S and P orbitals when creating bonds. We actually use what are called hybrid orbitals. Okay, so depending on how they mix, we get different shapes. So we'll start off with SP. So while we do this, I want to track what we have in terms of S and P. So in a regular atom, we have the 2s orbital, so we have one of these, and we have px, py, and pz. Okay, so we have 3 p's and 1 s. So to create what we call an sp hybrid orbital, we are going to take this s and one of the p's, and we are going to combine them into a hybrid orbital. So we have, for example, here the 2s, and we have, in this case here, it's the 2px. In this picture, the 2px. So if we take those two and we combine them together, we get this hybrid orbital. okay, where we have the out of phase here, and then we have the in phase constructive interference giving us this giant end to this lobe. Okay, so if we have two coming in, so we're going to form two what we call Sp hybrids. Okay, so we have two Sp hybrids, and then we have the two other additional P's that we didn't touch. So they are the green ones in here, the PZ and the PX. So look at what we sort of initially started with. Now look at those giant lobes here. So we have one pointing in one direction, and we have one pointing in the other. Okay, so when we have Sp hybridization, that gives us the 180-degree bond angles, or it gives us the linear shapes. Okay, so linear shapes come from Sp hybridization. Okay, so why this is important, and we're going to kind of talk about this a little more. Why not just mix them all? Okay, so these two here, these two P's that were the green ones here, these are left to form higher order bonds. Okay, so these, we could form a pi bond here, and we can form a pi bond here. So these two are left, and they typically are left to form pi bonds. Okay? So p orbitals that are unhybridized, like we see here, generally form pi bonds. Our hybrid orbitals, they form sigma bonds. So these are going to be along the axis. So again, we see the nucleus, or they are along the axis. So these are going to form sigma bonds. Okay, so mixing one S and one P to give us, again, increased probability of bonding, or a larger lobe for bonding here, gives us this shape here. Okay, so that's our first type of mixing. That's called, again, SP. So if we go to the next one, our next one is called Sp2 hybridization. So again, we're going to do the same thing. We're going to write S and P. Okay, so we know that we have one S and 1, 2, 3 P's. So you can probably guess what's going to happen here if it's called Sp2. One of these and two of these are going to be mixed together. Okay, so one S and two P's. So when we do that, we form three Sp2 hybrid orbitals. So if three come in, three go out. So the way that looks are these gold ones here in this picture. So we can zoom in a little bit here. Okay, so those are these larger lobe gold. So top view here. So again, we have the same thing where we create these lobes that have a small end and then a larger end. So you're seeing the large lobe here, the increased sort of probability or area or space for bonding. Right? So we have left one P behind. So in this one, it is purple. So that purple one right here, that's the P that's unhybridized. And this is left to form pi bonds. Okay, so typically we see this arrangement, and there's generally a double bond formed because you have left a P for a pi bond. Okay, so this gives us the 120 degrees. This hybridization gives us the shapes of 120. So for these ones, we see the trigonal planar. So the trigonal planar shape has Sp2 hybridization. Okay, we're three of those. And again, these are the sigma bonds. Those hybrid orbitals are forming sigma bonds. And then that leftover pi is left to form some sort of pi bond, so like a double bond. Okay, so let's go to now to the last one. So next or last, we have Sp3 hybridization. So hopefully you've guessed what's going to happen here. So in our atom, we have one S orbital, 1, 2, 3. So for Sp3 hybridization, we're mixing them all. Right? So we're going to form 4 Sp3 hybrids. Okay. Oops, the D. So 4, all of them mixed, all of them formed together. Okay, so we have S, Px, Py, Pz. Take all of them and mix, and we get 1, 2, 3, 4 hybrid orbitals. If we put them all together, we get the tetrahedral shape. So tetrahedral has Sp3 hybridization, and these form sigma bonds. So other things with tetrahedral as well have Sp3 hybridization. So the pyramid and also bent also has this hybridization. Instead of forming a bond in this hybrid orbital, it's just housing a lone pair if it's a pyramid or a bent. Okay, so all of them mixed together, they all form sigma bonds. So no pi bonds formed for the tetrahedral shape in for the most part for these scenarios. All of them are these sigma bonds. Okay, so let's take a look at some examples of bonding. Okay, so these are sort of drawn better than I could ever hope to draw for you. So this is looking at a triple bond. Okay, so this molecule here, let's change, go official black. So this is a hydrogen, a carbon, a carbon, a hydrogen. So it has a triple bond between them. So this is what this molecule is here, HCCH with a triple bond. So let's take a look at what that means in terms of bonding. Okay, so I'm going to undo all this. Okay, so let's take a look at, again, I'm going to draw it smaller up here. H, C, triple bond, and H. Okay, so that's our molecule. So if we didn't have this picture here, and we'll get to that, we would know that with this carbon, and we'll circle it in yellow. So if we were to look at this carbon right here, with those two electron groups, we would know that this bond angle is 180, and we would know this is linear. Okay, so what this means is we know the hybridization. We know the hybridization on this is Sp hybridization. Okay, so because it's linear, we do know it's Sp. Or hopefully by the time this lesson is done and you read a little bit in your book, you will know. Okay, so where does that come from? Okay, so we have our carbon, our hydrogen, and our hydrogen. Okay, so the sigma bonds are formed first. Okay, so these are the Sp hybrid orbitals. So for carbon here, we formed two Sp. So this is an Sp, this is an Sp. For this carbon, we have the Sp here and the Sp here. So those are giving us the sigma bonds. Okay, so since we're forming that triple bond, we had to leave the p orbitals behind to form that double and then triple bond. Okay, so let's mark out purple. So next we have another higher order bond. Okay, so that's coming from this blue, we'll call it the PZ, overlapping here and overlapping here. And then we know we're forming a triple bond. So we need that last p orbital above to overlap and below to overlap. So that's kind of what we're seeing in that here. So let's get my model out. Let's see if I have enough. Oh, that's so close. Okay, I'll have to use one small one. Okay. Okay, so this is what we have here. So we have our sigma bond, which I have drawn in blue. Oh, here, let's put our other bond there. Okay, so our sigma bond, which I have in blue, and then we have the other sigma bonds on this end, which are the Sp hybrids. Okay, so then we have the double or the two higher order bonds. So those are the p overlaps. So remember we have some pointing this way. So those p orbitals are overlapping like this. So in the picture, the ones I just did are green. So those green ones, those p orbitals, are overlapping above and below. So perpendicular. And then the ones here drawn in blue those are overlapping this way. So in front and behind, we're getting the overlap there. Okay, so you can have perpendicular going in front and behind and above and below. Okay, which is what we see in this picture here. So if we look at what we have, all of these ones I've drawn here in blue, those are all sigma. So we have 1, 2, 3. So we have 3 sigma. And then the ones in purple and green are pi. So we have 2 pi bonds. So again, we know these are going above, like out and in. Okay, so kind of hard to see. I did a lot here. Let me erase a lot of this so you can kind of go back and see the picture. Okay, so again, the ones where I can essentially just draw a line through this molecule, those are where all of my sigma bonds are happening. Okay, so the blue ones I have here, and then the pi bonds are perpendicular. Those ones are what I've drawn in the green and the purple here. So pi bonds here. Okay, so in higher order bonds, all single bonds are all sigma bonds. If you start adding like double and triple, the extra bonds essentially, those are pi bonds, and those are formed from p orbitals. Okay, so kind of that's important. Our pi bonds are formed from p orbitals. Okay, so since we had to form a triple bond, so we needed 2 p orbitals to overlap, our hybridization was only using one of those p. So we get sp hybridization for those sigma bonds right there. Okay, but for hydrogen, this is the 1s. So this is a 1s overlapping with the sp hybrid here, the sp hybrid here overlapping with the 1s, and then our purple one, again, that's a pi 2p, and the green one is also a pi 2p. Yeah. Okay, so what about sp2 hybridization? Okay, so this molecule here would be, that would be, let's see, draw it up here. H2C double bond C H2. Okay, so we have a double bond between the carbon and then single bonds with the hydrogen. So this picture is nice. It shows us the little sort of dots here. Okay, so let's do what we did before. So look at the shape we have here, 1, 2, and 3. Okay, so we have to leave 1 p orbital behind to form my double bond. So I have a trigonal planar shape here. So again, if you look at the carbon, it has 1, 2, 3 electron groups. So we know this is trigonal planar. Okay, but if we look at the bonding, we have those blue as hybrid orbitals. So we have the C, the H, the H, and the H. Oh, sorry, that's the C. Undo. And the H, and the H. Where this is, all these blue ones here for the carbon, these are the sp2s. And for hydrogen, that's the 1s. Okay, so 1s overlapping with sp2, where again, the lobes are very, very large, so we get good overlap there. But then we see this green here, that is our pi bond. So we would draw that here with green, that's our double bond. So here we have overlap above. Okay, so if I get my molecule back, that's exactly what we see here. Between the carbon, we have this, and then we have the green overlapping above and below to form the pi bond perpendicular. Okay, so if we count up what we have for bonding, we have 1, 2, 3, 4, 5 sigmas, and then just that double bond there, we have 1 pi bond. Okay, so that higher order perpendicular bond, that's our pi bond. Okay, so last with sp3, so this is like CH4. Okay, so this is CH4. Okay, so all of those are hybrid orbitals. Since we aren't forming a double or a triple bond, we don't need to leave any pi behind. So we're going to mix them together to make these giant lobes. So the more we mix together, the sort of larger the lobes we can make to get the best overlap. Okay, so that's what we're doing here. So all of these are sigma bonds. So if we were to draw CH4, our nice tetrahedral shape, like this. So no double bonds here, complete hybridization. We know this is sp3. So this is sp3. These are all sigma, so 1, 2, 3, 4. We have 4 sigma bonds, no pi bonds, and we have the sp3 hybridization, which gives us the tetrahedral shape. So if you know the shape, do you know the hybridization? Hopefully you've gathered from this the answer is yes. You have a linear shape, your hybridization is sp. If you have the trigonal planar, your hybridization is sp2. And if you have tetrahedral or the trigonal pyramid or bent, your hybridization is sp3. Okay, so let's give the hybridization, the geometry, and the bond angles around each carbon in the following. So we have this molecule right here. Okay, so let's look at this one right here. So this carbon, so that has 3 bonds to hydrogen. Actually, let's undo that. Okay, so if I were to draw this out, this carbon right here, I'm going to kind of, so we'd have H, H, H. So this is what we'd have if we drew this all the way out. Okay, so let's look at what we have. So we'll circle this one red. Okay, so we have all single bonds there. So this red one right here, this is tetrahedral. Okay, so we know it's tetrahedral because there's 4 electron groups, 1, 2, 3, 4. So the hybridization here has to be sp3 because we have that no double bonds, no triple bonds, all single bonds with the tetrahedral shape. That has to be formed with those 109.5 bond angles. Oops, let's put that in, 109.5. We get those from sp3 hybridization. Okay. So next, our next carbon is this one right here. Okay, so we have 1, 2, 3. We have 3 electron groups there. So we know that this purple one I've circled here has 120-degree bond angles. It's trigonal, planar. And to be trigonal planar with 120-degree bond angles, the hybridization has to be sp2. Okay, so we have formed 1, 2, 3 hybrid orbitals, and we've left 1 p orbital behind to form that double bond there. Okay, so let's go on to the next color. So we'll circle this carbon right here in green. So 1, 2 electron groups. So we know this is 180, and it's linear. And to get that linear shape, again, to form 2 pi bonds, this has to be sp hybridization. So you have to only hybridize one of the p's because you have to leave some behind to make those higher order bonds. Okay, let's move on to orange. So this one is the same. Okay, so 108. So we have 1, 2 electron groups. So again, we would expect 180 degrees. We know 180 degrees is linear. And then if it's linear and it has, again, this bond here, we know that the hybridization is Sp. So these angles tell us the hybridization. These angles come from these particular hybridizations. So if we can figure out the angles and the shape, we can figure out the hybridization of our carbon. And this is very important. This is going to follow you all the way up through organic chemistry and all that sort of good stuff. Okay, so let's do a sigma pi count. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 sigma bonds. And then I'm running out of colors here. How about, I don't know, gray? And then we have 1, 2, 3. We have 3 pi bonds. Okay, so 8 sigma, where we, again, expect those to be along the plane, and then 3 pi bonds, where we'd expect those to be perpendicular.